Everything's still working fine now? I got record on, whatever that means. Here we go.
Let's do it.
All right, AST training, basic Doppler radar. Okay, Shane.
All right. Introduction to Doppler radar. The most effective tool to detect precipitation is radar. Radar, which stands for radio, detection, and ranging, has been utilized to detect precipitation and especially thunderstorms since the 1940s. Radar enhancements have enabled NWS forecasters to examine storms with more precision this way. The radar used by the National Weather Service is called the WSR 88D, which stands for Weather Surveillance Radar 1988 Doppler. The prototype for the radar, which was built in 1988, as its name suggests. The WSR 88D is a Doppler radar, meaning it can detect motion toward and away from the radar, as well as the location of the precipitation areas.
Yeah. Now we know what the WSR stands for, 88D, right? That will be on a test later.
There's a test?
All right. Hey, I'm gonna start the video. If you guys hear a problem with this video, let me know right away.
Have you ever driven by the National Weather Service Northern Indiana and wondered, what is inside that big white ball? Well, today is your lucky day. Let's take a look inside the KIWX Doppler radar.
The KIWX radar is one of 164 radars located in the United States, Guam, and Puerto Rico. The IWX radar is shown here in the red circle. Each radar can reach out to about 280 miles, so they're placed in the United States so that most of the U.S. is covered by a radar. There are 3 buildings on the base of the radar tower that help control and power the radar. So let's take a look inside the first one of these buildings. The first building contains a computer that can control the radar remotely, as well as the energy source that powers the radar. The energy source that powers the radar is known as the klystron. This piece of equipment generates the radiation the radar uses to send out microwave pulses. The energy generated by the klystron is then sent up the radar tower through a series of wires and into a waveguide in the pedestal, which is located inside the radar dome. Here the radiation is then sent out through a series of microwave pulses.
There's a beautiful view from the top of our radar. We can see in every direction for a good 20 to 30 miles, including many of the beautiful lakes in the area. If you're a member of our electronics staff, you better not be scared of heights because the last steps up into the actual radar dome itself are very steep. The transmitted power continues up the waveguide, which is in the center of the pedestal, and goes up to the antenna where it is transmitted out to detect precipitation and other objects. The parabolic dish is 28 feet in diameter, and the dish and pedestal together weigh several tons. Due to the weight distribution of the dish on one side, there's a counterweight pictured here, which acts to balance the weight of the dish. This animation demonstrates exactly how a radar works. The pulse is sent out where it then detects objects such as precipitation, and power is returned to the radar where it is then processed and turned into the radar image you see on a screen. The reflected power is collected by the concave portion of the parabolic dish. We can adjust the radar to employ several different scanning strategies, depending on what type of storm environment we have. We can change the speed that the dish moves and also change the elevation levels in which slices are taken. Inside of the radar pedestal is where the radar's motor as well as the waveguide is located. The area inside the radar pedestal is very small, but our electronic staff have to go inside of here several times a year to do things such as cleaning out major components of the radar or also fixing issues with the motor. Inside of the pedestal is where the waveguide takes the signal back down to the ground where it is processed into the radar imagery that we see. Now that we have seen all of the components of the radar up in the dome, let's head back down to the ground.
Let's take a look inside the second of the 3 buildings at the radar complex. Inside this building is a large diesel generator. This generator will start up and run when commercial power to the radar is disrupted. Now let's take a look at the last of the 3 buildings at the radar site. This building houses the uninterruptible power supply, or UPS. UPS ensures a continuous flow of power through the radar site between commercial power disruptions and the activation of the backup generator. We hope you enjoyed the tour of the KIWX Doppler radar. Thank you for joining us.
How radar works. The basics of radar is that a beam of energy, called radio waves, is emitted from an antenna as they strike objects in the atmosphere. The energy is scattered in all directions, with some of the energy reflected directly back to the radar. The larger the objects, the greater the amount of energy that is returned to the radar. That provides us with the ability to see raindrops in the atmosphere. In addition, the time it takes for the beam of energy to be transmitted and returned to the radar also provides us with the distance to that object.
I got to get my mic back. You might want to turn your mics off unless you talk because we can hear all the noises in the back. Might want to mute your mics.
Oh,
Ready to talk.
204, you do have the ability to mute your mic. If you can please mute that, you are stepping all over 103.
Okay, ready? All right, go ahead, 103.
Doppler radar pulses have an average transmitted power of almost 450,000 watts. By comparison, a typical home microwave oven will generate about 1,000 watts of energy with a 0.009,843 second, 99843 times 10 listening period in between. I'm not doing math on this, so y'all are gonna have to get out your math books.
All right. Well, that's very interesting. I hope everybody's reading that because they're going to explain it a little bit on our next page, I believe. Look at this. Everybody can hear it. This is
Therefore, the total time the radar is actually transmitting a signal when the duration of the transmission of all pulses each hour are added together. The radar is transmitting for a little over 7 seconds each hour. The remaining 59 minutes and 53 seconds are spent listening for any return signals.
Now, did everybody see that? I don't know if you can hear me, but that's very interesting. I did not know that until I came across this.
Y'all hearing me okay?
I'm hearing you. I don't know if they got their mics on. Everybody?
Okay.
I can
We're
hear
hearing
I
you.
just
I
have
can turn my mic
muted.
back on.
You guys think that's pretty interesting? Only 7 seconds.
Absolutely.
Yeah, 7 seconds. Although all it's transmitting, the 59 minutes are of returning listening.
Yep.
All right, got another video here.
I'm sure you've probably heard the term Doppler before, but did you know the principles that we use in our weather radar today was developed more than 150 years ago? by an Austrian physicist named Christian Doppler. He found that the occurrence produced by a moving source of waves in which there's an obvious shift upward in the frequency for observers towards whom the source is approaching, and an obvious shift downward in the frequency for people for whom the source is moving away. Okay, let's simplify the Doppler effect for you. Think of a car on a road honking its horn. While the car is traveling towards you, you can hear the high-pitched sound of the horn. But suddenly, after it passes by, the pitch lowers and drops. Now, this is a perfect example of the Doppler effect, and this is how it's used in weather radar. The radar sends out a pulse of energy, which then reflects off an object, such as a raindrop. Now, some of the energy reflects away into the air, but the majority of it goes back to the radar, where it then calculates how far away the raindrop is, how intense the rain is, and which way the raindrop is moving in relation to the fixed radar site. Now that is where the Doppler effect comes in. We use the data sent from the most powerful radar in East Tennessee at the National Weather Service office in Morristown to our Storm Tracker 6 computer to show you the rain, sleet, and snow. But during severe weather situations, the wind speed and direction is what is the most important. If the wind in a small space is going away from the radar in one area and towards the radar right next to it, this can show that there's rotation within the storm, and that means there's a possibility that that storm could produce a tornado. Now, it can also show how strong winds are over a given length of a line of storms, and this can help determine whether the storm could produce what we call straight line winds. With Storm Tracker 6, we also have access to all the National Weather Service Doppler radars across the country, including Nashville, northern Alabama, southeast Kentucky, and northern Georgia, to give you the most complete storm coverage in East Tennessee.
The NWS Doppler radar employs scanning strategies in which the antenna automatically raises to a higher and higher preset angles called elevation slices as it rotates. These elevation slices comprise a volume coverage pattern, or VCP. Once the radar sweeps through all elevation slices, a volume scan is complete. In precipitation mode, the radar completes a volume scan every 4 to 6 minutes, depending on which volume coverage pattern, VCP, is in operation, providing a three-dimensional look at the atmosphere around the radar site.
Yeah, remember the VCP. We're going to learn more about. Matter of fact, if you look on your radar, you'll always see at the top, it's a VCP with a number after that, which is the mode that radar is using. There's a lot of different modes that the meteorologists can use to determine, what type of weather there is. They will switch the modes, and we will learn more about that.
A VCP consists of the radar making multiple 360-degree scans of the atmosphere, sampling a set of increasing elevation angles. There are two main operating states of the Doppler radar: clear air mode and precipitation mode. In precipitation mode, within the two operating states, there are several VCPs the NWS forecasters can utilize to help analyze the atmosphere around the radar.
This is important.
Doppler radar images are what has happened, not what is happening, because it takes time from several seconds to a few minutes to make the image available via the internet or updated on your local mobile device. By the time you see it, it's already old. It provides you a picture of what was happening, not what will happen in the next 2 to 5 minutes. Do not delay in seeking shelter should you see inclement weather approaching your location.
Yeah, I just wanted to make sure we all pointed that out because,
Sorry about the tunes in the background.
Okay. Yeah, what we're seeing is the history. We got to remember that. It could be 2 or 5 minute delay, and you know what can happen in 5 minutes. Check this out.
Fast facts. All modern radars are digitized Doppler radars. Therefore, the old-time radar sweeping line associated with analog radars is no longer applicable. However, some local television stations continue to fool you by showing sweeping radar on their broadcast. The sweeping arm is fake news, literally. The radar image itself may be valid, but the sweeping arm is added by a computer program after the image was created. Even if it appears an image updates once hang on, I gotta pop back in here.
Go ahead. You back on, Shane?
Give me a sec.
Yeah.
Even if it appears an image updates once the line passes any particular storm, the sweeping line is a computer generated and not real. Fake news.
See, even the weather people, right?
Yep.
All right, here, check the image out. Okay, Shane, thank you.
You're welcome.
Here, good job. So, yeah.
Thank you.
So we all have seen the radar images on the news during the weather, which we just seen in the previous video. So they're giving an image here, just some pictorial of a, that's what we're looking at here. The light bar, it's not a little sweeping arm that's rotating. I guess we're confused by watching old movies that we think we see that little line circling around and getting blimps. That's not actually how it works. So it's more like a flashlight. The beam gets higher and widens with distance. So we got to keep that in mind, how that works. All right. Now we're going to be talking about radios and pixels. Okay. I got my screen messed up here. Can you read that right here, Shane? Because I can't.
I can't either. Hang on a minute.
Right.
Review.
Yeah.
A line of pixels is called a radial. The pixels get wider with distance. When the data is smoothed, it gives you a false representation of the storm. And the other one is called a line of pixels is called a radial. Pixels are 3D boxes.
Okay. So anyway, we are familiar a little bit with this, but this is what the computer is picking up and generating to us. We got the pixels here. All these little tiny squares there. They're also called gates too. You've heard it referred to gates. I mean, you'll usually hear me when we're looking at a tornado signature. You'll hear gate to gate shear. So that's when they're real close together. So yeah, think of something like the spokes on a bicycle. Okay, so you have the radials right here. They're out with the lines. They're going this way, and the pixels are all what's in between there. Let me move on to the next one here. All right, this is like just showing if this is close by the radar. This area right here, 2 mile range. Look at it's got all these. Or this is far away. I'm sorry. Is this far away? Yeah, this is what a 2 mile radius would look like. You get here, when it's closer to the radar, look how many more pixels are in there. That's what they're trying to show us here. Pixels close to the radar are much smaller than they are far away. Another thing I wanted to run across right here, usually what we're seeing is composite. This might help you out too. Composite radar image. The difference between that and super res, which we're now familiar with super res, all the images, it almost does the same thing here. It would take, if you're looking at this with composite and they do super res, it would be twice as many pixels in the circle right here. So I kind of compare it to regular TV to high definition TV. That's what super res is. Somehow the computer can go there and even put more pixels in there to get more of a picture. So that's what the difference is, because we're looking at composite radar on the news. Okay, so just trying to give it an idea here. Look at the pixels here. See how much farther bigger and wider they are? Well, over here, you can't see the star, but the star here, here's where the station is, the weather station, or the Doppler radar. And the further you go out, the farther these pixels get apart. And you did hear mention about smoothing. You know, like on your, the computers will smooth that out. And a lot of times they say, once you smooth it, you're not getting the correct information. But supposedly somewhere over here is where the star is. So if we're looking close to the storm cell, look how much better it is compared to where it is when it's farther away from the radar site. Okay, now we have another thing. Oh, here you can see where the radar. Here's where our radar station is. The storm is 4.7 miles away from the radar. The beam height is 0.2 kilofeet. Instead of 0.5, I don't know why they said 0.2. But it's showing, you know, if you're close to the, we got to understand that when we're close to the cell, to the weather station, we're getting a good idea of what's going on. Now, the farther we get away, this storm is 126.8 miles from the radar site. The beam height is at 13.9 kilofeet. And see how we're pointing up into the storm. I guess some of us are used to that, but we always want to visualize it. The farther away, here's our outline here, right at the end of the area right here. They're picking up the storm, but we're looking way up, and that's past the mid-level area too. It's probably closer or a little bit higher than the mid-level area. So you're only seeing what's up high in that cell. Okay, what happened to my arrow? Here it is. Okay, now we have, on a normal day, radar gathers data even when the skies are clear. Okay, a new image comes in every 4 to 5 minutes. So this, actually, this was a video here. We can't play it because it was I screenshot it. But this whole loop took 1 hour. This is 1 hour and 20 minutes for for the radar loop that we normally look at. And again, the radar is spinning a lot slower now, and it's a lot sensitive. It's picking up the slightest amount of moisture in the air. Now, when they switched, now here it's severe weather day. This is interesting. Radars are switched into fast mode. Remember we were talking about the VCP? There's different modes for different speed, for the dilts and everything. One of the things I think I might tell you later, I'm a little familiar, is what they call sails. That's when it's really spinning fast and you're getting data, especially at the lower level, a lot faster than normal. So a new image, when it's in that mode, a new image can come in every 1 to 2 minutes, and the storm appears more anomalous. I can't even say it, but you know what I mean.
Ominous.
Yes. All right, here, let's give this a try. Here's, I think, our last video here. Then we'll take questions.
Welcome to Skywarn, severe weather training from NOAA's National Weather Service in Bismarck, North Dakota. I'm John Paul Martin, your warning coordination meteorologist. In this segment, we'll talk about Doppler radar. Doppler radar is a very important part of the National Weather Service warning decision-making process. Here's a picture of the Doppler radar outside of your National Weather Service office in Bismarck. Doppler radar sends energy out and it listens. Sends energy out and it listens. On the right-hand side is inside the radome, the Doppler radar dome. This dish is 32 feet in diameter. It goes around in a circle, sending energy out and listening. Once it completes one revolution, it stops, shifts up a little bit, and goes around again. Again, sending energy and listening. Stops, shifts up a little bit more, goes around again, so that we're taking slices of the atmosphere. The energy from the radar goes out in a horizontal pulse and then a vertical pulse. This way, we can get a better idea of the size and shape of the object that was hit, and then determine if it was a raindrop, snowflake, hailstone, or dirt or smoke in the air. This is called dual pole or dual polarization, vertical and horizontal. There are different modes we operate the radar in. There's clear air mode, where on a sunny day or a day with no precipitation, the radar scans only the lowest levels of the atmosphere. During precipitation or thunderstorms, the radar is in what's called a precipitation mode, and we scan more layers of the atmosphere to give us a better idea of the extent in the vertical of the precipitation or the thunderstorm.
You know what I mean?
There are a few radar limitations. The first is the cone of silence right over the radar. As a thunderstorm moves over the radar does not sample the whole thunderstorm anymore. It can't see the whole thunderstorm, so it may appear weaker. As the storm comes out the other side of the radar sees the entire storm again, and it may appear as if the thunderstorm grew stronger, even though through the cycle it did not increase or decrease in intensity. Another limitation of the radar is that the Earth is curved, and so the farther the energy goes away from the radar, the higher up the energy is in the sky. So at greater distances from the radar, the energy is at higher levels in the atmosphere. There are some gaps in radar coverage. It does not mean along the Montana-North Dakota border. It does not mean that there's no radar coverage. It means it's limited from the surface of the ground up to about 10,000 feet. The coverage is more limited, again, the farther you go away from the radar. Here's a drawing, a schematic of a supercell thunderstorm. Every thunderstorm has air that moves up. We call that the updraft, and air that moves down called the downdraft. Under the updraft, any precipitation here is being lifted up into the thunderstorm. It's falling out here under the forward flank downdraft. Again, under the updraft, the motion is upward into the storm, so very little or no precipitation falling there. Rain and hail falling here under the downdraft. There's another area of sinking air in a supercell thunderstorm called the rear flank downdraft. This is what grabs the circulation out of a thunderstorm, the rotation out of a thunderstorm, and brings it down to the ground in the form of a tornado. So keep that diagram in mind as we look at this thunderstorm over Grant County, North Dakota. Again, the energy sent from the radar was sent out. The energy hit something, energy came back to the radar, and it painted a picture. Here's the scale from on the bottom of the screen, from light blues all the way up through the purples and white. This is called base reflectivity, a reflectivity image. The energy reflected off of objects and came back to the radar. Small raindrops return a little bit of energy to the radar. The radar paints them blue and green. Large hailstones, especially large wet hailstones, return a lot of energy to the radar. The radar shows those on the high end of the scale in the dark reds, the purples, and the whites. So this base reflectivity depicts the intensity of precipitation from energy returned, shows precipitation, boundaries, and non-weather targets like smoke. Most of the time, this is what you see when you look online for radar or on television. They show the base reflectivity off the lowest slice from the radar. This image is off the Bismarck radar and depicts smoke from a grass fire. The wind is from the northwest, and so the smoke from the fire near Cannonball on the Standing Rock Nation is going to the southeast, across Emmons County and into South Dakota. Again, this Doppler radar is so powerful, it can detect smoke and dirt and dust particles in the air. Another image we get off the radar is base velocity. This is showing us how fast things are moving in the wind, and we can infer from that the wind speed. If the radar determines the object is moving toward the radar, it's painted green, and if it's determined it's moving away from the radar, it's painted red. Again, green is toward the radar and red away, and so this day we have a northeast wind over the radar site. The wind is coming from the northeast and going to the southwest. Another important display off the radar is the storm relative velocity. This compensates for storm movement and makes it easier to see the wind pattern in and around a thunderstorm. In this radar image, we see The radar is off to the right of the image. It's the Minot Air Force Base radar located near Deering, North Dakota. The radar sent energy out. Energy hit something. Energy came back to the radar. The radar determined the motion here was away from the radar and here was toward the radar. You can see this broad circulation away and toward the radar. If we look closer, you can see that we have these reds right next to the greens and blues. This is tight rotation, tight circulation inside the thunderstorm. This is actually a tornado. If you were near Bow Bells, North Dakota this day, you saw this large tornado. This is what you saw with your eyes, and in this image is what the Doppler radar shows. The National Weather Service, outlined in yellow here on the radar screen, had a severe thunderstorm warning for this storm, and outlined in red, the red polygon here, was a tornado warning on this storm. Again, base reflectivity and storm relative velocity can be used together to get a better idea of the storm structure in a thunderstorm. Here's our forward flank downdraft where precipitation is falling. Here's our updraft area where you see a weak area in the radar returns. Again, the updraft area. And back here is our rear flank downdraft, pulling circulation out of a thunderstorm and down to the ground. And indeed, there is a tornado in this image near Joplin, Missouri. Again, the radar is off on the right of the screen. The red is motion away from the radar. The greens and blues towards the radar. You can see this large circulation with the thunderstorm. And if we zoom in, you can see this rotation, very tight rotation. Again, away from the radar, toward the radar, right next to each other. This was a tornado near Joplin, Missouri. Again, the radar has limitations. Storms that develop on top of the radar or move over the radar may appear weaker or to weaken, when in reality they may not be weakening. Showers off in the distance that are small, the radar energy may go over the top and not even know the shower is there. The radar may not detect that rain shower. Terrain is also an issue with radar. As the energy swings around this side, most of the energy will go into this mountain and come back to the radar, and it'll paint a picture, the radar will paint a picture of the mountain and may not see, may not detect the rain shower beyond the mountain chain. But those limitations, there are a few, and they do limit the radar, but the benefits of Doppler radar far outweigh these few limitations. I want to thank you for watching, and I ask you to stay weather ready.
All right, I'm back. Everybody here?
Yep.
All right. I hope at least we got some basic understanding. What about questions? We got any questions out there? Or input? Give us some input.
Who's got questions? I think it was an outstanding presentation.
I think that was very knowledgeable. And again, getting back to the basics on radar, which we need to be doing often, because as we get new people in, we need that, and we often need to be reminded of it as well.
Yeah, it's like tonight, they even put it together. Yeah, I still learn. Hey, I had no idea about how much an hour. You know, it only puts out signals 7 seconds, and then it's all listening. That's pretty amazing. How about you there, Jenny? Any questions?
Nope.
Oh, okay. Kristen? Yeah, do we all know what, here? Do we know what WSR stands for? Anybody want to answer that part? What's WSR 88E stand for? Let's see if anybody was paying attention.
Weather surveillance radar built in 1988, and D stands for Doppler.
All right, let's give it up for 101. He's got it. Good job, 101. I couldn't tell you. How about radar? I couldn't tell you what, I mean, I seen it, but I don't remember what that was. Initials for radar.
I'll give someone else a chance to answer that one. I know the answer, but I'll give someone else a chance.
Okay, anybody else know what the initials radar stand for?
I read it earlier.
Okay. And then go ahead, 101, help us out there because I don't remember it. I know it's something. But
Radio detection and ranging.
that's what it was, the ranging. So did we all learn about being fooled tonight by the our weather TV, a little arm rolling around that we're actually looking at the radar when it's computer generated, not even the true fact.
When you think about what the TV stations do with that sweeping arm, think about a 1960s war movie when you're looking at them with radar detecting other ships in the area.
Yeah, that's why they give us the image. That's the only way normal people can comprehend it, you know. That's pretty neat that all this time that such a thinking that radar when it's actually just computer. Okay, well, we did it. At least they gave us some free time. We were going to kick us off, but they was a button that showed up on my screen. I don't know if you did, so thank you for allowing us to continue. Any other questions? Or anything else? We can call it a night. Like I said, I can only put so much together because Zoom only allows so much time. Our next training session now, I'm going to start going in advance. We're going to learn more about the different modes. And I know a little bit about them, but I'm going to learn a lot too. So we will advance from here for the next session. Any questions?
Sounds good. Thank you for putting this together for us.
Thanks.
Thank you.
Really cool presentation.
Thank you very much. All I got to do now is figure out where I can hit. I tried recording and I hope this works. So I got to figure out if I can turn off the recording. So, all right. Good night, everyone, and we'll see you at our
Good night.
A week or two away, right?
Night, guys.
Good night, everybody.
Good night.